We're going to start off by talking about the common ion effect. Common ion effect is a shift in the equilibrium that caused by the addition of a compound that has an ion in common with the dissolved substance. The presence of a common ion actually suppresses the ionization of a weak acid or a weak base. So this, in fact, is a manifestation, if you will, of Le Chatelier's principle. And you can see that by the example they consider here of adding sodium acetate, which is a very strong electrolyte and ionizes completely in solution, to a solution of weak acetic acid. And so, in other words, the equations is shown in the bottom there. So acetic acid will, without the presence of added sodium acetate, is going to form an equilibrium between the anion of the acetic acid and, of course, the proton, which has ionized from the acetic acid molecule. And so, however, when you add a common ion, in other words, when we add acetate via sodium acetate, the effect of this, again, via Le Chatelier's principle, is that the added acetate is going to have the effect of shifting the equilibrium from the right back to the left, right, to rebalance the K sub A, the equilibrium constant, because equilibrium constant at a given temperature is a constant, right? So if you add more solution to the product side, if you add more species to on the product side of the equation, you're going to shift the formation back towards the reactant so that the K sub A has remained constant. The impact to the pKa plus the log of the ratio of conjugate base to acid. So you can make a base by adding, for example, equimolar amounts of sodium acetate and acetic acid. You have, by doing that, you actually form a buffer. And a buffer, in essence, resists changes in pH. There are many reasons that you would want to have a resistance in changes in pH, able to resist large changes in pH when strong acid or base is added. And a nice schematic of that is shown here, that if you take a buffer in the middle here, a buffer solution, equal molar amount of acid and base, and if you add, for example, to the right, if you add hydroxide ion, strong base, you are going to consume some of the acetic acid, the concentration in our concentration bar will go down, it will be depressed, and a corresponding increase in the conjugate base of acetic acid will occur and generate additional acetate. Therefore, you're buffering against the strong base. Similarly, if you add hydronium ions, such as you would get when you add aqueous hydrochloric acid or aqueous sulfuric acid, the base, the acetate, the conjugate base in that equimolar buffer system is going to react with the hydronium ion, and it's going to form a little bit of acetic acid. It's going to form a little bit, and it's going to take up some of the acetate. And because of the Henderson-Hasselbalch equation and the effect that has on pH, right? And you can calculate that. We'll show some examples. You reduce the impact of those strong acids and bases with your buffer. Okay. One other concept that we'll touch on here is and that is buffer capacity. You need a certain amount of acetate ions and acetic acid ions, a certain concentration of each of those species in order to have a buffer, okay? They do not have unlimited buffer capacity. In Hasselbalch equation, and that you can make a buffer by adding your acid, the weak acid, and the conjugate base, which would be a salt of the base, right? And you could add equal molar amounts, and you can create a buffer by simple addition of acid and base in equimolar amounts. Addition of a strong acid to a buffer schematically is shown here. The buffer solution of 4 point, it's around what, 4.7, and what it shows is that, and this is our acetate buffer, it shows that you can add moles, okay, you can add moles of HCl, and those, as long as you don't add too much HCl to outrun that buffer capacity, the buffer solution is going to maintain a very controlled pH. Whereas in comparison, if you added that same amount of HCl to just water, the pH is going to dramatically drop away and become very acidic with just small amounts of HCl addition. So this illustrates very nicely the capacity of an acetate buffer system. Titrations. In a titration, a solution of accurately known concentration is gradually added to another solution of unknown concentration until the chemical reaction between the two solutions is complete. The equivalence point is the point at which the reaction is complete. An indicator is a substance that changes color at or near the equivalence point. And the way we will actually do this in our laboratory, we're going to slowly add base to an unknown acid until the indicator changes color. And that's considered a titration. And when the indicator changes color, that is an indication that you have titrated, if you will, the unknown solution to an endpoint, and then you can convert that to an equivalence point and determine accurately the amount of unknown solution or unknown acid in your solution if you're titrating the acid with a base that has a known concentration. That is a titration. Okay. We can also use a pH meter, and I believe that we will actually use a pH meter in one of our labs coming up. So we'll have more opportunity to actually see how a pH meter works. Okay, the first titration to review with you guys is a strong acid, strong base titration, and it looks like an S curve. That's all it looks like. And where the y-axis is the pH, okay? So we're titrating a strong acid. Okay, so we're starting out with a strong acid. So it's going to have a very strong, very low pH rather, strong, low pH before the addition of any titrant. And now we're going to titrate that with a strong base. In this case, we're titrating HCl, which is our solution. We're titrating a solution of HCl with sodium hydroxide titrate. And what you see in your titration curve, if you're doing this with an actual pH meter, is you'll see that the pH remains relatively low until you get very close to what we term the equivalence point. At the equivalence point, and this is the key feature here, at the equivalence point, the number of moles of acid has been completely and exactly neutralized by the moles of base that you have added with your titrant. It's as straightforward as that. It's as simple as that. And so that equivalence point, if you know the concentration of your base titrant, you can quantify the acid, the unknown amount of acid, strong acid, in your solution. And that's what this graphic illustrates. Similarly, you can titrate a weak acid. A weak acid starts out with a much higher pH than a strong acid for obvious reasons, but the fundamental of the titration is exactly the same. If you're titrating a weak acid with a strong hydroxide base, you will still reach a midpoint or an S curve, an inflection point, which is referred to as the equivalence point. So again, at our equivalence point, the number of moles of hydroxide from your titrant is going to exactly equal and have neutralized the moles in your unknown weak acid solution, and therefore you can use that as a base of quantifying the weak acid in your system. Similarly, you can titrate a strong, you can titrate a strong base with a strong acid. I'm sorry, this is a weak base. I'm sorry. You can titrate a weak base with a strong acid, and that is what is shown here. The weak base in this case is ammonia. Ammonia, of course, reacts with protons from HCl to form ammonium, right? To form ammonium ion. And the proton in ammonia, therefore, makes the proton reacting with ammonia makes ammonium. And you will reach an equivalence point, just as we've talked about earlier, and you will be able to quantify the amount of weak base, unknown weak base in your system by knowing the concentration of added strong acid titrant. Indicators change color when at a certain range in pH. Okay, indicators are very useful when you do not have a pH meter. They're very useful to visually identify this via an endpoint. They're used to identify and quantify the amount of unknown acid or base in your solution. And the amount of indicator color change relates to in fact, the extent of acid-base neutralization that has occurred with your indicator. The acid form of an indicator has one color. The base form of the indicator, or the neutralized form of the indicator, has another color. And as long as that color change falls within the steep rising or steep part of the slope of your titration curve, if you will, as long as you're in that steep regime, the color change of your indicator will be a good predictor of the actual equivalence point. And there's a number of indicators as shown here in this table 16.1. Here's a solution of red cabbage extract, which is an indicator. And it goes from red, presumably this is on the acidic side, would be left, and it goes through a series of colors until it gets very, very yellow on the highly basic side. Yeah, that's right, low pH would be the red, and then as pH goes to the basic side, it becomes yellow. Okay, titrating a strong acid with a strong base, another view of the how to select an indicator. And again, that indicator must change its color within the highly changing part of your titration curve. In this case, it's the highly rising part of that strong acid base titration curve. So methyl red has a pH range that falls within the steep part of this slope. And therefore its pH change range is consistent with being able to accurately identify the endpoint of this particular titration. The same thing for phenolphthalein. The phenolphthalein goes from white to red within the steep rising part of the titration curve. So methyl red and phenolphthalein would work, thymol blue will not, okay? Now, only just another view of this, and I drew some lines here, but the volume of hydroxide, okay, between the just initially rising part of your titration curve and the almost finished rising part of the titration curve, that is typically just a very small amount of volume, maybe a drop or two, and it causes a very dramatic change in pH. Certainly for a strong acid-base titration, it causes a very strong rise in pH. And because of that, and because we, again, reviewing the fact that the methyl red changes from red to yellow on the slope, right? It's red, it changes from red to yellow, and we can look at the pH range of what, about 4.5 to maybe 6 or so. And for methyl red, 4.2 to 6.3 is this change. Yeah, that's very consistent with the graph. Same thing for phenolphthalein. It's still very much within just that drop or two of change, which happens to be for phenolphthalein that color change is around between 9 and 10. And let's go down here, phenolphthalein, well, 8.3 and 10, I didn't eyeball it quite right, but still you get the point that that's where the pH change occurs. pH change that occurs with the color change, and it gives you an accurate, if you will, endpoint that pretty closely is going to approximate the true equivalence point, okay? We're going to shift gears. We're going to move forward and talk a little bit about solubility equilibria here. This is an example of silver chloride in equilibrium with silver ion and chloride ion. So silver chloride is a solid, and it does not dissolve very much in water. It's what we call sparingly soluble, okay? And it produces some ions of silver and chloride, but on a concentration basis, it typically is very low. The solubility product of a compound is the product of molar concentrations of the constituent ions, each raised to the stoichiometric power in the equilibrium equation. KSP is equal to the concentration of silver ion times the concentration of chloride ion, just as we would have done when we introduced the concept of equilibrium constants. Silver chloride is a solid, so it is not included in the KSP, okay? All right, so let's just go through some examples. Magnesium fluoride dissociates sparingly to magnesium and fluoride. KSP is equal to the concentration of magnesium, times the concentration of fluoride, and that's squared. The reason it's squared is because of the stoichiometry of that reaction, right? When mag fluoride dissolves, it liberates 2 fluoride ions. When silver carbonate dissolves, it liberates 2 silver ions in 1 carbonate. KSP is silver ion concentration squared times carbonate concentration. Calcium phosphate, when it dissolves, produces 3 calciums and 2 phosphates. The KSP, therefore, is equal to the concentration of calcium raised to the power of 3 times the concentration of phosphate, and that is raised to the power of 2. Again, it's we're taking the stoichiometry of our chemical reaction, and we are creating we are writing out our KSP based on the stoichiometry of those species that are dissolved into solution. Now, dissolution of an ionic solid in aqueous solution. Now, we've got a Q value, just like we had Q in the introduction to chemical equilibria, right? Q is not the equilibrium constant. It can be any value that you want for it to be within limits, of course. But Q, if Q is less than KSP, in other words, if we don't have enough silver ion and chloride ion to fully saturate, well, it's by definition a non-saturated solution. So in principle, we could put just enough silver ions and chloride ions into a solution, right, so that it doesn't dissolve. And because of that, you can have an unsaturated solution. There'd be no, I'm sorry, I said that wrong. You can put just enough, a tiny amount of silver ion and chloride ion into the solution so that it does not precipitate, okay? You keep the concentration below its level of saturation. That is an example of Q being less than KSP. You can saturate it, in which case you have an equilibrium between the ions and a solid, but just at the equilibrium point, you would call that solution just saturated. You would just be on the cusp of permanently forming a solid. And then as Q is greater than KSP, you're going to go into a supersaturated solution, in which case you are going to have bulk continuous solid particles of silver chloride in the solution in equilibrium with, again, the silver ion and the chloride ion. And that is, of course, an example of precipitate formation, or having a supersaturated solution. Solubility products of some slightly soluble ionic compounds are shown in table 16.2. And you see how very tiny these numbers are. Aluminum hydroxide, 10 to the minus 33, very, very tiny numbers representing very, very slight solubility. All the way to silver sulfates, 10 to the minus fifth. That's still not very soluble, but it's much more soluble relative to the aluminum hydroxide, and so forth and so on. And there are large tables of compilations of ionic compounds in various literature resources that we can use as references when we need them to find a KSP value. Okay, relationship between KSP and molar solubility. So this is an interesting exercise that allows one to convert the concentrations, if you will, of ions that is partaking or participating in a dissolution reaction with a solid. And if you consider those concentrations as S, you can come up with a number of relationships between KSP, okay, and S, or the molar solubility, okay. For silver chloride, if you put S into the as a concentration of silver and S as the concentration of chloride, of course, if you just start out with silver chloride, you're going to produce a chloride for every silver ion you do produce, right? So therefore, S is perfectly fine to put in that equation, and you put that into your KSP equation, and you find that S is equal, or KSP is equal to S squared, or S is equal to the square root of KSP, and so forth and so on. Let's just go down and pick this lead fluoride. One lead is going to produce two fluorides, so you have S and 2S. KSP is therefore equal to, do the math, for S cubed, and S is equal to, therefore, the 1/3 KSP divided by 4 raised to the 1/3 power, or the cube root of KSP divided by 4, right? And all the way down to calcium phosphate. Calcium, again, is going to liberate 3 calcium. Calcium phosphate is going to liberate 3 calciums and 2 phosphates, right? For every molecule of calcium phosphate that dissolves. And therefore the cation is going to be represented, you're going to have 3, right? 3S for every 2S anion. You plug that into your KSP, right? And of course there's raised to the power. It would be 3 times 3 times 3 is 27, times 2 times 2 is 4, so 27 times 4 is 108. And of course, the 3 and the 2, the power of S, or S raised to the power of 3 and the power of 2, is going to give you a combined S raised to the power of 5. And that's the relationship between KSP and solubility, molar solubility, for calcium phosphate, okay? Common ion effect in solubility. The presence of a common ion decreases the solubility of the salt. And again, the way I think about this conceptually is it follows Le Chatelier's principle, right? If you add, if you have a solution of silver chloride and you add silver nitrate, the silver nitrate is going to completely ionize. And that is going to add silver ion, or it's going to add to the product side of that dissolution reaction. And what does Le Chatelier say is going to happen? It's going to force it to go back to the left. So you're going to form more silver chloride by adding that common silver ion to that solution, okay? Just a quick example here, and I think we have just talked about that. The solubility of silver chloride in pure water is as listed. We did a calculation. So this is just the bottom line summary of a calculation that we'll do shortly. the lower solubility is in the presence of silver nitrate is reasonable. You can predict the lower solubility, right, using Le Chatelier's principle. Adding silver ions shifts the equilibrium to the left, decreasing the effective solubility of the silver chloride. You're going to take more of the chloride out of the solution and therefore decrease the silver chloride. pH and solubility. Okay, the presence of a common ion decreases the solubility. Insoluble bases dissolve in acidic solutions. And again, you're driving reactions. You're just driving the reaction to the right. You're using Le Chatelier's principle. Insoluble acids dissolve in basic solutions using Le Chatelier's principle. And all it is think about the dissolution of magnesium hydroxide going to magnesium ion and hydroxide ions. If you add acid to this, are you not going to force, you're almost titrating, if you will, the hydroxide that formed from the magnesium hydroxide, you're titrating that away with your strong acid and making water. And because you do that, you're going to shift that reaction to the right. And therefore, you're going to improve the dissolution or improve the solubility of the magnesium hydroxide, okay? So, yeah, and this example is an example that goes through that and goes through a nice calculation of showing that. But in essence, at a pH of less than 10.45, because again, the POH was calculated from the KSP, right? The POH was calculated, or the hydroxide ion was calculated. POH is 10.45 at a P. I'm sorry, the POH was calculated to be 3.55 by converting the hydroxide ion to the minus log of hydroxide, or POH. That gives you a corresponding pH of 10.45. 14 minus 3.55 gives you 10.45, right? pH plus POH is equal to 14. All right, so therefore, as long as your pH is less than 10.45, as long as you're more acidic, right, than 10.45, you are going to make water. You're going to make water. You're going to lower the hydroxide ion concentration. That's going to increase the solubility. In contrast, if your pH is greater than 10.45, you're going to raise the hydroxide ion concentration and therefore decrease the solubility of the magnesium hydroxide. So again, the point being is that pH has strongly impacts the solubility of sparingly soluble solids that are hydroxides, primarily hydroxides and oxides that will ultimately form hydroxides in water. So that's an important point, and it's used, of course, as you can imagine, industrially. One of the biggest usage of this is in industrial HVAC boiler systems, systems and boiler systems, both of which use lots of water to modulate temperature. And because they typically use lots of river water in big industrial systems, that river water has a degree of hardness that produces calcium and magnesium hydroxides as insoluble precipitates on the walls of the boiler or the HVAC system, the cooler. And that precipitate dramatically reduces the effectiveness or the efficiency of the heat exchange process itself. So it has to be removed periodically. And so there are chemicals that can safely acidify that water temporarily and clean off those insolubles and get rid of what we call scale. Okay, that's just one example of many of where you would use this type of technology. Complex ion equilibrium solubility. A complex ion is an ion containing a central metal cation bonded to one or more molecules or ions. Okay, and this is an example of cobalt complexing with chloride. Now we've just gone through a complex ion experiment in the laboratory, and it's very similar to this conceptually. Chloride, 4 chlorides are going to react with the cobalt and form a tetrachlorocobalt species. The formation constant or stability constant is the equilibrium constant for the complex ion formation. K sub F is products over reactants, just like all equilibrium constants are that we talk about, right? And so as KF gets bigger, the stability of that complex gets bigger, right? Because it's on the top of that fraction. So is a more stable complex with the ions that were added is going to be a larger K sub F. Hence it's called formation constant. Okay, and then the last thing I wanted to talk about here is there are rules that one can use, an analytical chemist can use to try to selectively separate metal ions from solutions. And you can use solubility product types of thinking and science in order to selectively precipitate some reagents from solution. So for example, if you have group 1 containing I think the idea here is that if you have all of these ions, you would go through a process of selectively removing these reagents and filtering them to quantify them, right? You would selectively remove them by controlling the precipitation reagent. So if you have all these ions together, you would first remove group 1. You would remove that using HCl, because it creates insoluble products for the group 1 cations, and they're going to fall out. You can precipitate them out and then filter them. Similarly, for group 2, you're going to use hydrogen sulfide. These group 2 cations form very insoluble sulfides. Similarly, you can use that was the H2S in the first example was in an acidified solution. The H2S for group 3 is in a basic solution to yet remove further ions from that solution, okay? So you can continue to go through this and remove group by group metal ions from complex solutions based on the careful choice of precipitation reagent creating selectively insoluble compounds. And that's shown again here as a way to remove up to 4 different groups of species. And it's a very, very fundamental old school analytical chemistry, but it's just as effective today as it was when it was developed, over 50 years ago. Another aside for ions, as we're talking about cations, ions create color when they are heated to high temperature in a flame. Lithium, sodium, potassium, copper are beautiful examples of the different colors that one can get. And you may have very well done this in your Chemistry 1 class. This is just a wonderful example of the atomic emission spectra that results when heating atoms, metal atoms and ions to very, very high temperatures in a flame such that you get electronic ionization event occurring. And that is the end of this chapter. We're going to follow this part up with actually problem solving on the whiteboard as a part 2.